Yeah, okay, so I wanted to say a little something about the Cauchy integral formula for derivatives that we proved last time. So remember, you have this thing, right? You've got your open set, you've got some disk whose closure is inside the set, and you've got some point z0 inside that disk, right? And there's a formula for the nth derivative. That is, you can take the integral of f over zeta minus c0 to the n plus 1 d zeta, right? Over the boundary of the curve oriented positive, right? And we proved that, by just showing the case, getting the first derivative by showing that the difference between the difference quotient and this formula went to zero as went to zero as h went to zero. So Stein does it in a slightly different way, and I just wanted to clarify something about it that might not have been completely clear to you. So Stein says Stein's proof basically says, well, let's just use the formula on the difference quotient, right? Right. So take the difference quotient and then just use the original Cauchy integral formula on it, right? This is going to be 1 over 2 pi I f of zeta over zeta minus c minus h e zeta minus the formula evaluated as z. Right, everything over h. Right, and then combine those two things together. Right, you get 1 over 2 pi I f of zeta over h, and then you get this difference, right? 1 over zeta minus c minus h minus 1 over zeta minus c d zeta, and then you combine these two guys together, right? And you get h over the product, right? And then the h's cancel out, right? The h's cancel out, right? Right. And then the point here is that, the point here is that, so we have our curve C, right? And so zeta is on C, Z is inside there, right? So there's a minimum distance from Z to the boundary, right? There's a minimum distance called D from Z to the boundary. So you know that zeta minus Z is bigger than that distance, right? And then the second thing you can assume is that h is within a disk of half that radius. Okay, so that so z plus h is going to live inside here. So you can assume that the distance from zeta to z plus h is bigger than, say, half of that distance, right? Right. So, right, because we. Okay. So what's the point here? That the point here is that if we look at the integrand, right, we're hoping that what's the point? The point is that we want to take the limit, right? So ultimately, we're going to take the limit of this whole thing as h goes to 0, and we're hoping that we can pass the limit inside, right? The reason we can pass the limit inside is because we're going to have uniform convergence here, right? If we have uniform convergence of this, then it's legal to interchange integration and limit. Okay, so that's really the key. The key is that the key step is key point is that this function here, as h goes to 0, this function converges to its limit uniformly. Right. That's what allows you to pass the limit under the integral, and then get the formula, get the desired formula. Right. F of zeta over zeta minus z squared d zeta. Right. That's what allows you to, in essence, differentiate under the integral sign. Right. Right. When you have your initial formula, f of z is given by this. And basically what's happening is that you're taking the derivative of the left-hand side, and we're allowing yourselves to differentiate under the integral sign and get this thing. Differentiate under the integral sign with respect to z and get this. Okay. So you have to justify this. Like, why does this thing converge uniformly, right? So you say, well, look, if you look at the difference. So why? If you look at the difference, it's just a calculation using those observations on the far right there about the distances. Right. So you say, well, look. This is controlled by the size of f over zeta minus over the size of zeta over z, and then you end up just by algebra again, the absolute value of h over the product. Okay, so you get this sort of bound, right? Just algebra gives you this bound, right? And then this thing is zeta ranges over c, and f is continuous, so this is bounded by some there's some bound for that by the extreme value theorem again, right? And then each of these things, right, is bounded below. Each of these terms in the denominator is bounded below by something, and so 1 over them are bounded above by 1 over those guys. So we get 2 over d cubed from that, and then we get h, right? And so what's the point? The point is that no matter what h you have. Well, the point is that the point is that this thing can be controlled as h goes to 0 independently, right? As h goes to 0. So that gives us the uniform convergence, and that allows us to switch the order. So that's the point. Yeah. Okay.
What would break if our integrand was not uniformly continuous? Oh, sorry.
If we didn't have uniform convergence there, then we wouldn't be able to pass through. Actually, you can't do that step. So like this you can't just always pass a derivative through an integral. You can't always differentiate under the integral sign.
Is that because we'd have some behavior like 1 over x or something like that?
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Got it.
Yeah. So I mean, to give you kind of a trivial example, right? Like, I don't know if you probably saw this example when you encountered uniform convergence, but if you have some function that like fn is, say, so this is a simple example. It's say like the characteristic function of n plus 1. Right, so it says, well, I'm going to give you a value of 1. I'm going to give you a value of 1 on that interval, and I'm going to be 0 elsewhere. Right? Then, of course, the integral, right? If you take the limit of the integrals, right? Well, each of those integrals is 1, right? But if you take the integral of the limit, right? Well, the limit is 0 for every value, right? For every x you take, the limit is 0 as n goes to infinity, right? So this is 0, right? So you can't interchange limit and integration, but. So you have to have this condition of uniform convergence of the integrand. Okay, so yeah, so that's what I wanted to say about Stein's proof, which is basically the same, but I think it's good to pull out this uniform convergence, to highlight the necessity of uniform convergence. Okay, so the next one we're going to do is the more application. Chapter 2 is basically just applications of Cauchy integral formula. So the next thing we're going to do is to show that if you're roughly speaking, that if you're holomorphic, then you're analytic. Okay, so as usual, you have an open subset of C, and you have if F is holomorphic, on omega, then for every disk D, and let me call that D centered at some point. I'm going to specify the center and radius. For every disk such that the closure is contained in omega, we have a power series expansion. F has a power series expansion. Power series expansion about Z naught in D. Okay. And the proof of this is use Cauchy integral formula. Right? That's like, don't do this on an exam, but basically this is the answer to every problem. So, yeah. Yeah, although I did have a classmate in graduate school who was gutsy enough to do this sort of thing. He'd just say like, use Cauchy Riemann on the exam. There was I don't know if this will amuse you, but there was a guy at Princeton a couple of years ahead of me, like 2 or 3 years ahead of me, named Shin Mochizuki. You should look up this name. He's actually super famous now. Shin Mochizuki. I think he's at Kyoto University.
Is he the
ABC?
Yeah.
Yes, that's him. Yeah, that's the guy. Anyway, so he was like 2 or 3 years ahead of 2 years. I think 2 years ahead of me at Princeton. He finished in 3 years, and then as I recall, so Princeton doesn't accept its own students to its graduate program. Like most places don't accept their own students to their graduate programs, but they accepted Shin Mochizuki to their graduate program. And as I recall, he finished his PhD in 1 year. Yeah, in 1 year. But anyway. The story about him, that there are all sorts of stories that sort of floated around, but one story, there are stories about all sorts of, because there are all sorts of interesting people at Princeton, like Nash, for example. Nash was there, of Nash embedding theorem fame. But the story that floated around about Shin Mochizuki was that that on his homeworks he would write, "This is trivial." Right? So like instead of working out the problem, he would say, "This is trivial," and he would just turn it in like that. And the graders knew how smart he was, and they would just give him full credit for it. Yeah, but yeah, no, he, if you look him up, you'll see that he was actually smart enough to call all of that stuff trivial and get away with it. Yeah. Okay. Okay. So the answer to this question is use Cauchy integral formula. So. Okay. So we want to show that there's a power series expansion. So you say, well, look, for every z in the disk, we have the Cauchy integral formula. F zeta is equal to C zeta. Right? Okay. And then the trick is to rewrite. We want a power series expansion in Z naught, so we just rewrite this thing using a power series expansion in Z naught. So you say, well, look, we're going to rewrite this thing as 1 over zeta minus Z naught minus zeta minus Z naught. Okay. Right. So we work in the zeta minus Z naught with a cleverly chosen 0. Right. We've subtracted a Z naught. We've added on a Z naught. Right. Okay. So then we factor out. Right. We factor out the zeta minus Z naught. Right. We get 1 over 1 minus Z minus Z naught over zeta minus Z naught. Right. And then we use the geometric series expansion. This is 1 over y minus something, right? And so that we can rewrite that guy as summation z minus z naught to the n from n equals 0 to infinity, right? And that's that converges as long as the absolute value of this is less than 1. But of course it's less than 1, right? Because z naught is the center here, z is some point, right? And the distance from the edge to z naught is bigger than the distance from z to z naught, right? So that's definitely going to converge. Okay. So okay. So let's point here. So now we're going to we want to use again uniform convergence. Okay. We're going to use the uniform convergence of this series. So we choose an R that's bigger than the distance from z to I'm sorry, that's not right. We choose an R, so choose R such that z minus z naught over, we choose R for this thing, over zeta minus z naught is less than R, is less than 1. We know that this thing is smaller than 1, right? Our z is fixed, and this is the same. So, right. So this we choose an R so that this is smaller than 1, and then we know that this thing converges uniformly inside there, right? That's the point. So then this thing converges uniformly inside, converges uniformly there. right? It converges uniformly because sorry, I'm going crazy. It converges uniformly by the Weierstrass test. Okay. Right. I shouldn't say it converges uniformly there. All I mean to say, this series converges uniformly by the Weierstrass test. Okay. So. So what does that allow us to do? Right now we have f of z equals 1 over 2 pi I integral f zeta summation z minus c naught to the n zeta minus c naught to the n d zeta, right? And from 0 to infinity, right? And so this thing converges uniformly, and so we can pull the infinite sum out. Okay. So by uniform convergence, we can pull this guy out. Right? We get the integral f zeta minus c naught to the n. Sorry, there should be a +1. Sorry, made a mistake. There should be zeta minus c naught out here. That gives me a +1 here. Okay. This term is of course independent of zeta, and so I can pull it out of the integral, right? Okay. And that gives me the power series. Okay. So hold on for 1 second. Let me make sure that I haven't lied to you. That's a constant. Okay, I don't think I've lied to you, but okay. Is there a question? Yes, Nico.
When we say the sum converges uniformly,
Yeah.
Converges uniformly to what?
Converges uniformly to this.
I see.
Yeah. But it doesn't matter actually. All we care about is that this sum converges uniformly, right? Because we don't want to go back to that. We don't want to go. We're coming from that, right? We start from here. We get this expression as a series, right? And then we want to use the uniform convergence to make this into a power series. Right. That's what we do. Okay. 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 Good. Everybody okay? Okay. There's something that's bothering me, but let me. I'll get back to you next time if I've lied to you. Yes.
And so, is this a way to prove like Taylor series, or would it be a circular argument?
Yes. What this is saying is that yes. I mean, what this is saying is that every holomorphic function has a power series expansion,
Yeah.
right? Right. And at the same time as Jaden pointed out last time, it also gives you the Cauchy integral formula for derivatives simultaneously, maybe with a tiny bit more work. Yeah.
Which is why I was asking, like,
Why not do it this way?
Yeah.
Yeah, that's a good question. Yeah, I'm not sure. Yeah, I thought about it, but I couldn't come up with any like I don't see anything that the original proof does that this proof doesn't do also. No?
When we're saying that sum converges uniformly, we're saying that like in terms of zeta being the variable that's allowed to vary, not z, right?
That's right.
Okay.
Yeah. Yeah,
Okay, cool.
that's right. Yeah, okay, let me get back to this. I may have something to say to fix next time, but yes, that's right. Okay, so the next thing we're going to do is the so-called identity theorem. Which says that if F is holomorphic on a region gamma, and you consider the set of zeros, so let capital Z denote the points where F vanishes. Okay. So if Z has a limit point, then F must be constantly equal to 0. This is a really shocking statement about how constrained holomorphic functions are, right? So, right, if such a thing were true for real functions, what that would be saying is that if your function is 0, right? If your function is 0 on any interval, then your function must be 0 everywhere, right? Right. That would be very restricted. Yes, say it.
So, are we basically utilizing the fact that the holomorphic function is analytic to get this result?
Yes.
Okay.
Yes, that's what we use. Yeah. So it's true, right? If your function is analytic, right? If your function is analytic and 0 in some interval, I'm sorry, and then if it's 0 in some interval, then it'll be 0 within the disk of the radius of convergence about there. Yeah. Okay. So here's the proof. Let Z0 be a limit point of the set of zeros. Okay, and choose any disk centered at Z0, such that the closure is contained in the set. Okay. So, right, by the theorem we just did, we know that we have a power series expansion about Z0, right? Okay. There's a power series expansion about Z0, and so so we claim that F must be 0 in that disk. Okay, so the proof is by contradiction. By contradiction, right? Suppose not. Then we know that there is some coefficient that's non-zero, right? One of these coefficients has to be non-zero. So take the first one, right? then let a sub m be the first non-zero coefficient. Right? And you rewrite f of z as a sub m z minus z naught to the m times 1 plus something. Okay, right. So you're just you're just factoring out you're just factoring out the first m. You're just factoring out the mth term from this. Okay, right. So so you get something like this where g of z goes to 0 as z approaches z naught. Okay. Okay, and then you use the fact that this is the limit point. So you say, well, look, take the sequence wk in z that converges to that z naught, right? Well, f of wk is 0 always, right? And then on the right-hand side, a sub m wk minus z naught, the m result is non-zero, right? Right? This is a non-zero term, right? Wk is going to z naught, but doesn't reach z naught. And so we get something like this, right? But as the wk's go to z naught, right? This term is going to approach 1, right? And so you have something non-zero, times something that's non-zero equaling something that's 0, and so that's a contradiction. You have to say today's proofs are not the most exciting, but okay. So so what does that give you? That gives you that right, that whenever you have, right, so you've got your omega, you've got your point z naught, and you can take any disk around it, and you get 0. Right? Is that right? It's going to be 0 in that small disk. Oh, of course. Sorry. Okay, but that's just for this limit point, right? Sorry, I was going crazy for a second. Okay, right. So that's just true for that limit point z naught. It's not true for some arbitrary point. Okay. So how do we show that that we're 0 everywhere, right? How do we show that we're 0 everywhere? I'll show you two ways of doing this. Okay. So there's the way that Stein does it, and there's another way that I don't know. You might like. Wait. Yeah. Okay. Just making sure. Yes. So there's another way that you might like, which is the following. You say, well, look, both rely on the connectedness of omega. So I don't think I said it, but omega is a region. So it's a connected set, connected open set. Okay. So so what about other points? Some other point, arbitrary z in omega. Okay. So omega is connected, and so you know it's path connected. Okay. So right, here's my z naught, here's z. You know that there's a path connecting z to z naught, right? So let omega z denote a curve from z to z naught. I'm sorry, from z naught to z. It doesn't matter. Okay. Okay. So we had some theorem before that if you have a compact set and then a closed set that doesn't intersect it, then there's a definite distance from your point to that closed set. Remember that I call this the distance formula, right? Right. So we know that right, there's some right, for all points zeta on that curve, we know that the distance from there to omega complement is bigger than some value. Right? So there's some positive distance that that the distance never breaks. Okay. Okay. So choose points. Choose points z0, z1, z2 through zn, where zn is the last, is zn is z, on the curve, such that the distance between consecutive points is always smaller than delta over 2. Okay. Okay, so you get these points. The distance between them is always smaller than delta over 2. And then take a disk of radius take a disk of radius delta about the first point. Okay, take a disk of radius delta about the first point. We know that the function is 0. The function is 0 within there. Right, right, and so right. So the function is 0 at the second point. Right, the function is 0 at right. So let me write this out. Take a disk of radius delta about z0. Notice it contains z1. And we already know that that the function is 0 inside there. Right? Because we know that we just showed that at a limit point of the zeros, if you take any disk about it, then it's going to be, the function is constantly 0 inside there, right? Okay, but that tells you that at z1, you see that f of z1 is 0, and in fact, z1 is also a limit point of the set of zeros, right? And so you can take a disk of radius delta about z1, right? And you know that it's going to be the function must be constantly equal to 0 there, which tells you that at z2, that it's 0, and that Z2 is a limit point of capital Z, and so on and so forth. And so you can just bootstrap your way over to the end, and you get that you get that Z, the value at Z must also be 0. Yeah,
How do we know Z0 is a limit point?
Z0 was that limit point we started off with, right?
Gotcha.
So
Oh, okay,
we,
okay. And I see, you're saying like once we have one, we
Yeah.
build a neighborhood, and then the next one is a limit point?
Yes, exactly.
Gotcha,
Yeah,
okay.
right. So Z1 is the guy from the first part of the theorem, right?
Okay.
Z0 was, Z0 was
Right,
the
W
limit,
continuous.
limit point of Z,
Okay, thank you.
right? So we know that any disk around it is going to be constantly, it's going to be 0, constantly equal to 0 there, right? But then this guy's inside there, and because it's an open set, it's not, that guy is also a limit point, a limit point of Z, and so we can say the same thing about it, and so on and so forth. So that's one way to see it. I think that's the way that's done in these very old books by Conrad Knopf. It's like there's like these tiny books that contain a lot of complex analysis. That's what we used when I was an undergraduate. Okay. Now, Stein's way of doing it is it's basically the same, uses basically the same facts, but in a slightly different way. So Stein's proof as opposed to Knopf's proof. Let U be the interior of Z. Okay. In case you're not familiar, this one means interior. So let U denote the interior of the set of zeros. Okay, right. It contains Z naught, right? Because Z naught was contained in that disk, right? And of course it's non-empty. Okay. Oh, I forgot to mention something, which was that just one comment here. Z naught. Remember, Z naught was a limit point. Z naught was a limit point of Z. But remember how Z was defined. Z was defined as the zeros. Z was defined as the zeros of F, right? And if you look at the definition of this set, this is a continuous function, right? F is a continuous function, and so Z is closed, right? Z is closed because you're taking the pre-image of a single point, right? That's a closed set. So you're taking the pre-image of a closed set, and the pre-image through a continuous function of a closed set is a closed set, right? I hope that's clear, right? Like this Z is pre-image of a closed set, right? F is continuous, so the pre-image of a closed set is closed. So you know that Z is closed, right? So Z naught actually is inside of Z. That I actually needed here when I was using the path connectedness. Right? You could have said, well, how do you know that Z naught is inside of Z? Anyway.
Isn't it that the pre-image of every open set is open?
Yeah, and also closed sets. Yeah, because if you take the complement, it's also
Would it be
true.
that the image of? Oh, okay.
Yeah.
Yeah.
Yeah. Okay. Okay. So let me come back here. So we have U as the interior, right? U is open because any interior of a set is open, right? So since it's an interior. Okay, and now we'll show that U is closed. by noticing that you say, well, look, if z is a limit point, if z is a limit point of u, then there's a sequence z sub n in u such that z sub n converges to z. Okay, but by continuity, f is the limit as n goes to infinity of f of z sub n must be f of z. Right? That's you know, whenever you have a continuous function, this is true. That's almost a definition of continuity. Right? But f of z sub n are all 0. Right? So what does that tell you? That tells you that f of z must be 0. F of z is 0, which tells you that z is in u. Right? Because we've just shown that any limit point is in the set itself. Okay. So so now we use connectedness, right? Since omega is connected, we know it can't be separated, right? It cannot have a separation. Right? There can't be two open sets whose union, two disjoint open sets whose union is omega, right? If we write omega as u disjoint union u complement, we see that that this guy is open and closed, right? So this guy must be open and closed, right? And so if this were non-empty, then we would have a separation, right? So that tells us that U complement must be empty, because otherwise we'd have a separation. Okay. So what does that tell us? That that tells us that that the whole set must be the zeros. That zeros are the whole set. Okay. 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 So corollary, kind of obvious corollary, right? If you have two functions, f and g, holomorphic on a region omega, and if the set where f and g are equal, if this set has a limit point, then f and g must be equal to each other everywhere. Okay. Of course, but consider the difference. Okay. 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 So that's that for the that's that for identity theorems. The next thing we're gonna here's another consequence. So this is like a sort of a converse to Cauchy croissant. Morera's theorem. Okay. So you have D, an open disk. You have D, an open disk, and you have a function. You have a continuous function. So it says that if for all triangles contained in D, the integral over the boundary is 0, then F is holomorphic. Okay. So the right. So what's the proof here? Can somebody just tell me how you prove this? Why is this true? No.
Like it's similar to one of the previous theorems that we were trying to prove, where basically like we pick a particular point and then we wait, am I lying to myself?
I do
I
it all the
find it
time.
a proof, but and then like we draw that thing, and then that like we draw a horizontal line and a vertical line
Yes,
up to our point,
yes,
then a horizontal and a
yes.
vertical line up to our point plus
Yes,
h.
yes.
And then we like show that a bunch of things are 0 to
Very
find that
good.
it's just the integral along the line.
Good, you were not lying to yourself.
Okay,
Yes.
cool.
Yes, yes, exactly. Right. So remember, once we got Cauchy croissant, we were able to show that that would force the function to have a primitive, right? And so, if we have this condition, then we ensure that f has a primitive, right? The proof, as before, we get that little f has an antiderivative. Big F, right, in omega, right? I'm sorry, in D. But then, it's once differentiable, right, because it's an antiderivative, right? It's a primitive. But we've just seen that once differentiable implies infinitely differentiable, which means that f is certainly once differentiable. It's also infinitely differentiable. So, right, f is infinitely differentiable. Right, and so f is also. So that's nice, pretty trivial. A nice consequence. So here's a nice corollary of Morera's theorem. So you have some sequence of functions. You have some sequence of functions. If when all of the Fn are holomorphic, and 2, on every compact subset of omega, suppose we have that f sub n converges uniformly to some function f. So this is the symbol for converges uniformly. So if you've got holomorphic functions that converge uniformly on every compact subset, then the thing that they converge to is holomorphic. Okay, and we're going to do it just by using Morera's theorem, right? So, right, we want to show that so by Morera's theorem, it suffices to show that for every open disk D such that D bar is contained in omega, and any triangle T contained in D, that we have the integral of f over T is 0. Right. Once we have that, then Morera's theorem tells you that you're holomorphic. Right. That's what Morera's theorem says. Okay. But D bar is compact. So we know that f sub n, by hypothesis, we know that f sub n converges to f uniformly. Right. So we have uniform convergence, but uniform convergence allows us to switch integration and limit, right? So the limit of the integral of the f sub n's over the boundary of the triangle equals the integral of the limit right? But this is the integral of f over the boundary, right? And this is 0. Right. Each of these guys was holomorphic. So each of these integrals is 0. They're just taking a limit of a bunch of zeros, right? And that by uniform convergence does it for us. Okay. Everybody okay? Any questions? Yes.
How do we extend this from these disks to the whole
We're, you're holomorphic. Holomorphicity is a local thing, right? So for every, we're showing that we've got holomorphicity within that disk, right? So,
Okay.
right? Yeah, we can just do that at every disk. Sorry, compact. Right, so as long as you know that on every compact set, you've got uniform convergence, then your limit then holomorphicity is preserved. Okay, I think this might be the last thing I'm going to show. Okay, so last thing. So further. So under the assumptions of the previous, further. The derivatives of the f sub n converge uniformly to the derivative of f on every compact subset of omega. Okay. And thus every derivative, right? The second derivatives will converge to the second derivative, and so on and so forth. the proof basically just uses the Cauchy inequalities. So use Cauchy inequalities. Okay. So okay, so we're trying to show uniform convergence of the derivatives on every compact subset of omega. So it's, I'm going to say for simplicity. So in the assumptions of the previous one, we said that we had uniform convergence of the sequence on every compact subset. For simplicity, I'm just going to say that we have assume that we have uniform convergence of the original functions to f on all of omega. It's not hard to go from there to the more general case. So let me just assume it. Stein assumes it. It's not hard to go. It's not hard to do. So let omega delta denote all the points in omega such that the closed delta disk around z around that point is contained in omega. Okay. So right, so you fix some distance omega, right? You fix some length omega, and then you look at all the points for which the delta ball around it, the closed delta ball, is actually contained in omega. You call the union of those centers omega delta. Okay. So right, as omega gets smaller, then we edge out closer to the boundary. Right. It's basically, you know, everything whose distance to the boundary is greater than or equal to is greater than omega delta. Excuse me. So it suffices to show that that Fn prime converges to F prime on each, that we have uniform convergence on each of these guys. Okay. And this we can do just by using Cauchy inequalities. Right. So how? Right. We want to show that we've got control over the difference, right? So let z be inside omega delta, and let's consider the difference Fn prime of z minus f prime of z. Well, by Cauchy's inequalities, we know that that's controlled by the supremum, right? Cauchy's inequalities says that, you know, the derivative is controlled by the supremum of the function over the curve over the radius, right? So we know that this thing is controlled by the difference between the original functions over the, as you range over the delta curve centered at, the delta circle centered at z, right? Divided by the radius of that circle, right? Right? But that is controlled in turn by the difference over the difference over omega delta, right? Right. We want to create a bound that doesn't depend on z, because we want uniform convergence. Right. So you say, okay, well, we know that Fn converges to F uniformly on omega delta. Right. In fact, it converges uniformly on all of omega, right? So, you know, given any epsilon, there exists an n past which, such that if you're past that time, then f of n minus f is smaller than, say, delta epsilon. Right, for all zeta in omega. Right? And so that gives us that, you know, we can find, right, so we can find an n past which this difference is smaller than epsilon. In other words, we have uniform convergence. So, and thus, Fn prime minus f prime is smaller than epsilon for all z in, so uniformly for all z in omega delta. Yeah, no.
Is the for all zeta in omega, why is that not omega delta?
You can say omega delta.
Okay.
Right, we had actually uniform convergence on all omega, so, but yeah, what we need is omega delta.
Okay.
Yeah. Fine.
Why are we able to take the supremum over omega delta instead of, is that the boundary of our delta neighborhood, that C dz?
This is, yeah, this is this.
Yeah, because I thought omega delta is the set of points, you know, or at least delta from the boundary.
Yeah.
But,
yeah.
yeah.
So, yeah, that's, I should say this, actually.
Okay.
Thank you.
Or maybe we could, yeah, I think this probably works. I was wondering, like, we could take C delta over 2 as Z, and then maybe we could use omega delta over 2 in this stage. Okay, cool. Thank you.
Yeah, no, good, thanks. Okay, now we're done. Okay, that's it for today.